Have you ever wondered how a shaft made in India fits perfectly into a hole manufactured in Germany, without any trial, without force, without adjustment? That silent agreement between machines across the world is called ISO 286. Today, we're going to break it down, from absolute basics to real-world applications, so that by the end of this video, you won't just remember ISO 286, you'll understand it. If you're a mechanical engineering student, a CAD designer, or someone working in manufacturing, this standard is not optional. It's the language of precision. So let's decode it, step by step. Imagine this. Factory A makes a shaft with diameter 50 mm. Factory B makes a hole that is also 50 mm. Perfect, right? Wrong. Because no machine is perfect. Even a tiny error of 0.1 mm can cause assembly failure, excessive wear, noise, and vibration. So the real question is, how much variation is acceptable, and how do we define it globally? That's where ISO 286, published by the International Organization for Standardization, comes in. ISO 286 is an international standard that defines limits of size, tolerances, and the fits between mating parts. It answers three critical questions. What size can a part actually be? How much can it vary? And will it be loose, tight, or press-fitted? This standard applies to shafts, holes, and all cylindrical mechanical components. It works on two core ideas: tolerance grades, known as IT grades, and fundamental deviations, represented by letters like H, F, and K. Let's look at the math. Nominal size is what's on the drawing, say 50 mm. Actual size is what you measure, but we define limits, an upper limit, like 50.02, and a lower limit, like 49.98. The difference between them is your tolerance, in this case, 0.04 mm. Key takeaway: tolerance controls accuracy, cost, and interchangeability. Smaller tolerance means higher cost. Larger tolerance means easier manufacturing. Precision is always a balance. ISO 286 defines international tolerance grades called IT grades. They range from ITZO 1, which is ultra-precision for gauges, to IT 16 for very coarse manufacturing. For precision instruments, you'll see IT 5 to IT 6. For standard machine components, it's usually IT 7 to IT 9. Remember the golden rule: the larger the IT number, the larger the tolerance. This means a 50 H7 fit is much more precise and harder to manufacture than a 50 H11. Now for the part that often confuses students: fundamental deviation. This defines where the tolerance zone sits relative to the nominal size. We use a letter system. Capital letters like H, G, or F are for the hole system. An H hole means the lower deviation is 0. The hole never goes below the nominal size. Small letters like H, F, or G are for the shaft system. An HH shaft means the upper deviation is 0. The shaft never goes above the nominal size. This ensures predictability in every assembly. ISO 286 defines three types of fits. First, the clearance fit. Here, there is always space between the hole and the shaft. Think of bearings or sliding parts. A typical industry combination is H7 for the hole and G6 for the shaft. This ensures the part can rotate or slide freely without jamming, regardless of the manufacturing variation within those limits. Then we have transition and interference fits. A transition fit, like H7K6, can be slightly tight or loose, perfect for accurate alignment. But an interference fit, like H7P6, is where the shaft is always larger than the hole. You need force or temperature changes to assemble these. This creates a permanent, solid connection used for mounting gears or pulleys onto shafts without keys or splines. Most engineers use the hole basis system. This means you fix the hole size, usually using an H-type fit, and vary the shaft. Why? Because it's much easier and cheaper to manufacture different shaft diameters than it is to buy a dozen different specialized reamers for different hole sizes. The shaft basis system is only used when you're using standard-sized raw material shafts, like cold-drawn bars, to save on machining the outer diameter. Let's put it all together. When you design a gearbox and write 40H7 F7 on your drawing, you're speaking a global language. A manufacturer in Tokyo or Chicago knows exactly what tools to use, what the final size range must be, and exactly how that assembly will feel. No emails, no confusion, and no rework. That is the true power of ISO 286 in the modern industrial world. ISO 286 is the backbone of global manufacturing and the reason parts are interchangeable across the planet. If you understand this, you understand precision engineering. This is Simple Guyan signing off. Don't forget to like and subscribe, and comment ISO below for our exclusive fits and tolerances cheat sheet.